quantitative, ecological and the mathematical sciences into landscape decision making. Today we have quite a full day of science presentations, and we're going to kickstart that with two presentations. They're going to give us different perspectives on state of the arts in environmental modelling. And we're going to start off with Mark Rounsevell, who is Professor of Land Use Change at the Karlsruhe Institute of Technology in Germany. And he's also Professor of Rural Economy and Environmental Sustainability at the University of Edinburgh. And Mark's going to give his perspective on an overview of land systems modelling. So Mark, over to you.
Thanks, Paula. I'm assuming everyone can see the slides that are in front of me at the moment and that you can hear me clearly. That's great. Thank you. I'll bring my microphone a bit closer. Thank you very much for the invitation to speak at this meeting. I was asked to provide more of an overview of the topic of land system modelling, just to try and introduce you to some of the concepts that we use within that community. And I want to do that. I'm going to do a little bit of a historical tour as well, starting right back sometime in the past, to try and give you an idea of the evolution in thinking about how people reflected on modelling land systems. So, first of all, I think it's appropriate that we start with the landscape. And I've chosen this landscape for a number of reasons, partly because I'm actually sat somewhere in the middle of that red circle. This is Garmisch-Partenkirchen in the German Alps, south of Munich. And I just wanted to introduce you to the notion of land systems and what we're actually trying to achieve when we try to build models to understand these systems. So if you look at this landscape, you have all sorts of different land uses that are going on here. You have meadows at the bottom for hay production, you have forestry in the lower slopes here, you have semi-natural habitat at the top, which is forested. In the background, you have cropping systems, you've got urban development here, we have tourism infrastructure, these are ski lifts, you have ski pistes down through the forest here. So there's this enormous mix and range of different land uses. And of course, we all live within what is fundamentally a human-dominated world. So the real challenge of land system science and land system modelling is fundamentally about the human behaviours that explain land use decision-making. So within this talk, I'm very much going to be talking about how we try and build models to represent those processes of land use decision-making by the land users themselves. I know in previous talks, people have been talking about landscape decision-making with respect to policy decisions, and I will come back to that a little bit later on, but I'm fundamentally looking at how we think about the land users themselves. So, in the beginning, I always like to start talks with my first citation from 1809 or thereabouts. It's not entirely clear, actually. So this is David Ricardo, who's a British classical economist from the 18th, 19th centuries, and he introduced this fundamental concept, which we still use today in land system modelling, called land rent. Now, land rent is not actually the rent you pay your landlord to live in an apartment, it's the economic return that land accrues in productive use. So it's an economic concept. And basically what Ricardo was saying was that the best quality land would be used first in production, and it would be used in the way which was its most economically productive, best use of that land. And this enabled Ricardo to think about distributions of land use in terms of this concept of the economic return of land rent. So that was the sort of early thinking. I'm also showing you this just to try and emphasize that actually the notion of land system modeling and thinking about land systems has been around for a really long time. Yeah? And obviously it's evolved through time, and I'm going to show you a little bit about how that's happened, but they're fairly fundamental concepts that have been around for a while. Right, so this gentleman is von Thurnen. He was a German farmer and also classical economist, and he introduced a slightly updated version of Ricardian land rent theory using the simple function you can see here. So basically the left-hand side of this equation represents Ricardian land rent. It's looking at the productive potential through yields, it's looking at prices of the commodities produced from land and the costs of production. That's largely Ricardian. The right-hand side, however, introduces the notion of relative location. So in this case, it's also looking at the costs associated with the transport of land-produced goods to markets. So you have a notion not only of the economic productive potential of land, but also of its relative location with respect to markets. And this sort of bullseye figure you see here on the right is the type of outcomes you get from this type of modelling. It's very stylized, but basically what you're observing are bands of different land use classes with respect to, in this case, the central city, which is the location of the market. And actually you can see these types of patterns in empirical data of land use distributions. And as I'll show you a bit later on, it can all be explained by von Thunian theory. There are also other factors which come into play. But so far we've got the productive potential of land and we've got the relative location as being really important. But these sort of methods, whilst I'm starting at the beginning of the 18th century, they're actually still used today in many applications. I'm going to zoom forward now to this century, although only just into this century for this bit of work, still fairly old. And this is an example of how people use some of these Ricardian von Thunian principles in modeling land use distributions. This is an approach based on optimization and many different ways of optimizing in practical terms. This particular approach is based on linear programming model that looks at profit maximization. There are other goal programming models, for example, that might look at utility maximization, but it's looking at optimization also within different constraints, and those might be constraints in this case for the timeliness of field-based operations, because we're looking at an agricultural example here, or the availability of labor, or the availability of land. And in the simple example you can see in the maps on the right-hand side, which this is East Anglia on the top and the northwest of England on the bottom maps. And this just shows a simple comparison of the model distribution of wheat for observational data from math in those days and against the simulated data. And in this case, we're basically modeling each of these grid cells like it's an individual farm with an individual decision maker making those decisions based on optimizing the production potential. So of course, some of the drawbacks perhaps with these approaches is that they always assume rational economic behavior. And as I'll show you a little bit later on, that doesn't always work. They also assume perfect knowledge and perfect information, i.e. that the land user knows everything about the future evolution of prices, costs, and what the weather is going to do, which again is maybe a bit of an assumption. And it also assumes basically that the optimum use of land is the actual use of land in practice, which, as again, I'll show you a bit later on, is not always the case. And just to give you another example, this I think, Paul, you showed the integrated assessment platform on day one of this meeting, and this just shows another example. Actually, the rural land allocation box in this figure here is actually based on basically the model I showed you in the previous slides, which is a linear programming based model, which is used to do the land allocation here. And so, even in sort of up-to-date models, we're still using some of these sort of classical economic principles to try and help us understand patterns and distribution of land use. The map on the right just shows an example of distribution modeled forest land use. As Paul rightly pointed out in the presentation on the first day, one of the strengths of this type of approach is that we're looking not only at the direct land user decision making as represented through the linear program in this case, but also the interactions with other components of the environment. So the availability of water, for example, the availability of land in competition with urban land use, the evolution of crop yields, etc., protected areas perhaps, with respect to protection of biodiversity. So what we've got here is a model of an individual land user based on economic principles that's embedded within a context. And that context, in this case, is very much the biophysical context. But actually, we have to reflect on also other contexts within which individual land users are making their decisions. And importantly, we need to start thinking about the social context. And this is, again, I've now leapt back to the last century. So this is some really seminal work by a Swedish geographer called Hagerstrand, working out of Lund University, who produced this model in the 1960s, hence the slightly old-fashioned looking diagrams that I'm showing you here. And what Hagerstrand was trying to do was he was trying to understand why he was observing in his case study, which is this sort of small landscape region of southern Sweden, you can see on the right-hand map. He was trying to understand the uptake and adoption of a particular pasture management regime. And he was observing this management practice diffusing through the landscape. And that got him to hypothesize about the use of diffusion or knowledge diffusion as being a critical factor in understanding why farmers were making decisions about land use. So he built a model which is based on Monte Carlo simulation. He created for an individual farmer what he called a mean information field, which is basically a probability matrix with a distance decay embedded within it in terms of the ranges of these numbers that you're seeing here. And he was hypothesizing that the spread of information came from the physical interaction between individual farmers. That was, they were leaning over the hedge, talking to the neighbors, and explaining, yeah, have you seen this new great way of managing our pastures? And what that led to the uptake and the spread of that particular information through the farming community. So in the model, you've got a probability matrix, you roll the dice, generate a random number, and you can look at the next set of adopters. So the series of maps on the right just show a work-through simulation where you're looking at how this adoption of this management practice is spreading through the landscape through time. And of course, as you will know, most of you in the room as mathematicians, that what you actually observe as an outcome from this is a slow startup phase, then a period of exponential growth in the adoption of this land use, and then a saturation leading to a leveling out. You basically are creating a logistic curve based on this simulation approach. So really critical that we start understanding physical interaction between individual land users. But Haggerstrand went a little bit further. What he also began to observe was it wasn't just physical proximity between individuals which accounted for the flow of information and knowledge. He was also noticing that social networks were incredibly important, that actually people's different levels of social status were critical in the communication they had with others and the ways in which that knowledge was disseminated throughout the landscape. So in this particular example here, he was observing how larger farms were earlier adopters than intermediate and smaller farms, and he was hypothesizing it's because larger farmers tended to operate within similar social networks, therefore the knowledge was exchanged between them. So again, we're really finding now that in addition to the basic Ricardian economic principles, that there's some critical issues to consider here in terms of looking at relative location, distance to markets, but also relative location within social networks and social interaction in understanding the uptake of land use. So just take that a little bit further, when people were beginning to observe these relative interactions and the importance of relativity within space, then this opened up a whole new way of trying to understand land systems and a whole new genre of land system models, largely based, in fact, in these particular examples, based on a Cambridge mathematician, John Conway's Game of Life, which was a basic cellular automaton, which looked at the relationships through qualitative transition rules within neighborhoods between cells that were alive or dead. And the land system community adopted these principles and turned them into a representation of the land system by looking, rather than a simple two states alive and dead, looking at multiple state systems where those states are individual land uses or land use classes. And this is some of the sort of early work by a Belgian geographer called Guy Engelen, working with a Canadian geographer, Roger White, who had started to build these micro simulation models in gridded space, where they're looking at creating, you can see the functions in the middle here, they're looking at creating push-pull or attraction-repulsion functions that look at the interaction between individual land uses in terms of relative distance. So one quick example of that is, if you look at the top right, you've got tourism, and that tourism, the relationship between tourism and airports as another land use, is represented in this blue curve you see here. And of course, tourists don't want an airport on there right next to them because they're noisy and inconvenient, but you do want an airport at a reasonable distance. Hence you get this peak here because you want to get to your tourist destination. So they postulated different functional relationships between individual land uses and used the transition rules between those in a cellular automaton to try and look at the micro dynamics of changes in land use change. What the figure on the right shows is you have that micro simulation in the central set of maps, but what was quite interesting in some of this work is that they recognize that there are actually multi-scale issues that need to be considered as well. We had Felix on the first day talking about issues around scale, and that's critically important in modeling land systems. People are beginning to realize that it's not just the land user and the local context that the land user is embedded within, but there's also a broader set of issues. So in this case, it's very much looking at the supply and demand trends much more broadly. How many tourists are there? What's the supply of tourists, etc. And we have to consider those higher level processes as influencing the lower level micro simulations. So that's an important lesson that was learned from the cellular automata-based approach to land use modeling. And another example of this, again, Guy Engelen and Roger White's work. In this case, just because I've been using rural examples so far, this is just to show you a simulation of urban development. In this case, urban development in the city of Cincinnati in the US. And what you can see is you've got this is the simulated progression of the urban development of the city from the mid-19th century up until the last century. And actually, if you compare these types of simulated patterns with the observational data, they actually compare really quite well. So we're beginning to capture with these types of grid-based, transition-based models, pretty good representations of land use distributions. But, there's always a but, there is a drawback. They're largely based on graphical representations of postulated relationships between land use. They somehow don't capture the true essence of the processes that are underpinning some of those transition relationships. And that's where I'm going to slip into the last category of models. I'm trying to bring us a little bit more up to date, which are models that actually start to try to combine the whole range of processes and issues that I've been trying to explain to you so far. So broadly, this categorization of models I'm calling agent-based models, and there are others who are talking later on this morning who will give you more examples of this, which is great. I'm just going to give you one or two examples here. But agent-based models are trying to represent the various multiple dimensions of land use decision-making. They will look at economics, utility and benefit function-based. They'll also look at individual behavior in terms of motivations, people's social status, awareness of the environment, which we know from empirical social survey analysis are all important processes underpinning individual behavior, but also they look at social interaction, competition between individual agents, cooperation, the development of social networks, the exchange of knowledge. So some of the issues I was looking at a little bit earlier. However, having said that, many agent-based models, there are many examples out there, often look at how they represent these processes in different ways. There are decision tree-based approaches, there are niche models, which is the example shown on the right-hand side here. And there are many different examples of how to do that. And there's no consensus around what is the best way forward, and there may never be. But there are different ways in which we can do this, and we'll see one or two examples of this a little later. One of the great powers of agent-based models is because they're often rule-based and qualitative, is that they work really well linking into social theory and linking into empirical social data and social elicitation exercises. So that's really useful. The other thing to point out is in many cases to simplify agent models, they often adopt a typology approach. So what you see on the right-hand side here is the notion of agent functional types. So different individual agents that can be parameterized with individual behavior and then compete or cooperate within virtual space given a physical and socio-economic context. And we see how the distribution of agents and the commensurate distribution of land uses evolve through time and through space. A few examples. This is a simulation in Great Britain of the evolution of bioenergy crops, two crops, miscanthus and short rotation coppice. And as you can see, again, it goes back to this notion of spatial diffusion. There's an economic component, but also a social interaction component, a co-evolution of land use with the development of power plants, given as some red dots here. And what you see on the right-hand graph is the black line shows the logistic curve, which is the outcome of the simulation approaches for the bioenergy model. But I'm just comparing it here. It's rebased to zero, these two sets, with some empirical data based on the evolution of the cultivation of oilseed rape, which we saw in Great Britain over this period of time from about the late 1970s onwards. That also follows a logistic curve. That's empirical data. This isn't a true validation, but it does show that the types of behavior that we're modeling through these agent-based models does closely mimic the type of behaviors we are seeing from observational data of a different but individual crop in practice. So we're beginning to capture some of the realism. Another example, this is an example of urban land use modeling using agent-based modeling. And the interesting thing here is we can also look at how people's behaviors are not static. You know, the early classical economics were assuming that everyone was economically optimizing and everyone was doing exactly the same thing, and they do it all the time. In these examples of agent-based models, we see that we have an evolution through people's life cycles of how they change the behavior and their whole decision-making process. And that, coupled with the fact that individuals are different, mean that we capture enormous heterogeneity in terms of individual behaviors and their experiences contextually within the social networks within which they operate. And these are observed maps and simulated maps of the distribution of households in this is the coastal area of East Anglia in England. And another example, going up to a larger scale level, this is scenario simulations of a model called Crafty, competition for resources between agent functional types, which is looking at trying to model societal breakdown scenarios, which again, some of the more economically based models struggle to deal with that. This is a scenario analysis based on different socioeconomic change scenarios. The top one is a SSP1, is a nice, pleasant world where everyone's happy and equitable, etc. The bottom is a dysfunctional scenario where we get this very different, very heterogeneous pattern of land use coming out because people are actually going back to the land and having to become self-sufficient. It's almost going back to a situation as was 200 years ago. So again, you can get these very different outcome patterns from these types of models. I think I'm running out of time, so I'm going to skip through that particular one and just more or less finish with my last one or two slides, and just to see what can we do in sort of bring all of this together in sort of multi-scale modelling frameworks. And this is very much work in progress. I've presented some of this at the equivalent meeting last year, but it's still work in progress, unfortunately. It's an enormous task. This is the land system modular model, LandSim, where we're trying to bring together various of these notions of trying to understand land systems across scales, right through from the global to the sub-national down to 1 kilometre resolution scale levels. It tries to integrate biophysical properties through ecosystem modelling and biodiversity modelling. It's looking at using a climate emulator called Imogen to model the climate system. It deals with economics in terms of supply and demand trends, but also international trade and the flow of commodities around the world. And it's looking at the subnational scale as well in terms of using an agent-based model to look at more of the behavioural and social interaction processes that I was showing you a little bit earlier. And just a quick note for observation, there's a few people in this virtual room engaged in this, but we're currently trying to build an agent-based model of the UK based on the Crafty principles, currently under development, should be completed by the end of the year. So there should be some really interesting land use change simulations coming out for a wide range of land use classes later on in the year. So watch this space. And the last one just to add is, whilst I focus primarily on modelling the land user within these different types of systems, there's an emerging interest in thinking about modelling the policy process itself and institutional behaviour as an agency-based problem. So using agent-based models to model the actual policy decision-makings, looking at policymaker agents, monitoring the landscape, having objectives, having certain policy levers that can be implemented in order to change what they're observing in space. And I think Brett is going to talk a little bit more about modelling policy in a moment. So my final slide, just a range of conclusions based on what I've tried to show you so far. I'm not going to go in any detail through this, but just to highlight that there's a wide range of processes that we need to try and represent in modelling land systems across different scales that goes from everything from economics, individual behaviour, and particularly social interaction within social networks. There are many different ways of doing this and many different models. There's emerging interest in trying to endogenize the policy processes within these types of models, but we still need to make considerable progress in developing land system models in a number of different ways, and I've just listed a few of those in my penultimate bullet point. And of course, to highlight for all of you in the room that there is a major role for the maths and stats communities in supporting these advances by engaging primarily with the land system modelling community. So thank you very much for your attention, and I will finish there.
Thank you very much, Mark. That's an awful lot of information for people to take in over many different, not just decades, but centuries. Just a reminder to all the participants to go to the Slido link if they want to pose questions. The code is in the timetable, but many of you are obviously familiar with the process now because we already have quite a few questions already in for Mark, and we'll try and just get through a few of those now. So Mark, first question from Jan Dick was, how do you think social media may influence Hagerstrand's model?
Yeah, thanks, Jan. That's a fantastic question. Really good. We were challenged one time when writing a paper on modelling spatial diffusion processes by a reviewer to say, well, what's the empirical evidence for this? What's the basis for it? So we went away and actually did some empirical analysis and tried to look at whether we can see empirically patterns of social interaction, social networks, particularly within farming, but also in forestry communities. And one of the things we tested is exactly the question you've raised, that hasn't, the goalposts have probably changed. You know, farmers, foresters, other land users probably have different sources of information and access to that information that they wouldn't have had 100 years ago, social media being a really important case in point. Interestingly, when we looked empirically at the evidence base, we could not find any evidence to suggest that social media is so far affecting the ways in which farmers make decisions with respect to their interaction with social networks. So it seems that farming communities, at least currently, are still using more traditional ways of updating themselves about knowledge, about different agricultural practices. Whether that will change over the coming decades, I don't know, but that is certainly an interesting area for endeavour to try and explore some of those interesting issues.
Okay, thanks. And a slightly related question, again here from Cliff Dent, actually asking about how it's possible to validate against empirical data the kind of land use and knowledge dissemination models that you presented, particularly sort of going on into a little bit more detail about what you meant by models matching the real world well when you referenced it.
Yeah, again, it's a really good question. I could give you several presentations on the topic, possibly. Validation is always critically important with modelling. We do a lot of calibration of these models. Sometimes people conflate calibration and validation, but in some way we do need to confront these models with data and confront models with the data that weren't used to calibrate those models. And what we try to do in a lot of the models we build is to try and calibrate and validate the individual components of those models, and then try to explore whether the overall model behaviour is commensurate with what we know from empirical evidence and from reality. The really interesting thing, I think, in this case is that a lot of the agent-based models are based on complex systems principles thinking, and because of complex systems thinking, you know, in complex systems you've got non-linearities, you've got bifurcations, you've got all sorts of system properties that these models can simulate, but it actually means that the historical record, i.e. the past data that we call observational data, is actually only one realization of one past. And the past could have actually been really, really different. So if we think that validation is only about confronting our models and trying to replicate what happened in the past, that's not necessarily a fair validation of the model. The model may be capturing nuances in the simulated world, which just didn't happen to play out for whatever reasons in the historic world. So there's a really sort of philosophical issues around how do we compare these types of complex systems-based models with observational data, which of course, being data is a model anyway.
Okay. So one very quick last question, which is merged from several questions that are emerging over Slido. They're all around the idea of how you validate EVM over large scales and how you go about parameterizing those age types because of the difficulties in collecting the data to do so over very large areas. But also, is there a maximum number to the number of agent types? And if so, what would that be and why?
Yeah, so calibration can be done in a number of ways. I mentioned that one of the advantages, say, of agent-based models or qualitative-based models, rule-based models, is that they're very consistent with the types of social elicitation data that are collected, where people go out, undertake surveys with land users, ask them about their motivations and try and understand how they make decisions. So we can calibrate models on that basis. We could try and validate, or at least compare with observational data. Are we capturing the basic essence of the realism that's been observed from the past? That's what we try to do. It's extremely difficult to do that. And as the question is rightly pointing out, access to data sets, particularly at larger scales, is extremely difficult. I would love it in terms of calibration if we could really start putting together mega data sets of all of the social elicitation empirical experiments that have been undertaken out there, because there's probably enormous amounts of data that just aren't brought together, but could be really used to support the model calibration and development. And the last question was on the number of agents. Probably in technical terms now, in computing power terms, there is no limit to the number of agents that you could construct. You know, there are what, 7 billion plus people on this planet. Hypothetically, you could construct a model with 7+ billion objects in your computer program. In practice, you can't do that because you can't parameterize every single one of those individuals differently with different sets of behaviors, motivations, and decision strategies. In practice, that's why we actually build on typologies, because then we can begin to categorize types of behaviors in ways that are consistent with what we see from the empirical evidence base. So yeah, but otherwise, yeah, the model I showed in East Anglia with urban land use was basically modelling every household in East Anglia, so around about somewhere in the order of 500,000 to 750,000 households, something like that, as individual agents. And we have data to parameterize that from statistics.
Brilliant. Thank you again, Mark. You've given us a lot to think about, and hopefully the presentations from more of the quantitative social sciences will really elaborate on some of the issues you've raised later on today. So thanks, Mark.